Good morning. Today's lesson is all about translators. So it's how we go from a high-level programming language to the machine code that our CPU understands. So just been talking with year 12s about different types of CPUs and what it looks like for the machine code. And we did some research and we found that a modern Intel processor, a CISC processor, which you learn about at A-level, has over 2,000 different instructions. So things like add, subtract, multiply, divide, shift left, shift right, like over 2,000 different ones. And it's possible, if you know what you're doing, to write the assembler, the low-level code, to get absolutely every little bit of performance out of your CPU, but very few people know how to do that. We were looking at the reference guide, and the reference guide, going through all the instructions, is over 2,000 pages long. So it's obscenely complicated. To abstract away from that complexity, remember abstraction means hiding the unnecessary detail to focus on the most important thing. Well, the detail is necessary because the CPU needs to know how to function. And so the compiler, the bit that works out how to generate the machine code, needs to know that detail, but most of us don't need to know that. Most of you just want to write something like print or input or something in Python that does a lot by writing a very little. But I still want you to be aware of the process of how you go from the code that you write to either interpret that or compile that into the stuff that actually runs on the CPU. So what does a source code translator do? Well, it's a little bit like a translator in Mandarin or Cantonese or Portuguese. If you want to speak to somebody in a language that you don't understand, you can either spend ages learning it yourself, or you can pay or persuade somebody else to do it for you. So a translator will translate what you want to understand into something that you like to be able to speak in. And for us, it means we can translate from Python into the binary, the machine code that actually gives the instructions to the CPU. Why do we need to do that? Because we're not very good at writing out the binary to get the CPU to do what we want it to do. We want to write as little as possible, as fast as possible, which is why Python was invented. Python is an inefficient language. It is not going to run very quickly. But it is also a very efficient language because you can spend a small amount of time to write a small amount of code that does an awful lot. So companies save a lot of money by paying their expensive employees a lot, but they pay them to do the work in less time, rather than paying their employees a lot to do the same amount of work, but with a huge amount of code. If you're a software development company, you'd have to pay your software developers way more money if it takes them longer to write their code. So, sorry, a lot of waffle from me. We need to convert the text, the Python, the C#, the C++, from something that a human, a programmer can understand, into something that the CPU can understand. That's what a translator does. Why do we need to do it? Because CPUs don't understand Python. They don't understand C#. They only understand the binary or the machine code. So it gets translated. There are two types of translators, and they both convert from high level to low level. Big misconception time. Low level does not mean easy. Lots of people think we start learning programming in Scratch, so therefore low level means Scratch. That's not correct. Low level means assembler. It means low level of abstraction. Remember we talked about an ant crawling around on the floor at a low level. It sees a bit of dust and it sees it like a mountain. You're at a high level. You stomp around on your big two legs. You look down and you can't even see the speck of dust. You can only just about see the tiny little ant. You're interested in things like doors and chairs and pizzas, big things. High level means you're interested in big concepts, write a small amount of code to do a lot. Low level means you're interested in the detail, the performance, the memory management, timing. So, machine code is the raw binary. It just runs on the CPU. It doesn't need a translator. That's what the CPU understands. Assembly is low level. In order to get to machine code, you have to translate it using an assembler, which makes sense, doesn't it? Assembly requires assembling. You use an assembler to translate it into the machine code. Python and other high-level programming languages either use a compiler or an interpreter. Pause the video in a moment to have a think. Do you know if Python is compiled or interpreted, and what's the difference? So I'm sure the PowerPoint will go through the difference in a moment, but Python is an interpreted language, which is why it runs so slowly. If you imagine learning Chinese, and by Chinese I mean Mandarin or Cantonese or something, it's going to take us a long time to do. It's going to take me a long time to do. But once you learn it, you can have a fluent conversation and speak quickly. That's like a compiled language. So you have a huge program like, I don't know, Blender or something written in C, C++. It takes a long time when you press the build button. It might take several hours to actually generate the bytecode, turn it from your C or your C++ into the machine code. But once you've compiled it, it runs blisteringly fast because it's all running in the native language for the CPU, the machine code. If you wrote something like Blender in Python, it would be interpreted, which means every line of code would be run in Python. Now remember, the CPU can't understand Python, so you have to interpret it on the fly. You have to get that string, that text, the Python, convert it, which takes time, and then run it. So they both had their advantages. They both are the same in terms of you go from your source code through your translator, which is either a compiler or an assembler or a interpreter to generate the machine code. But there are differences. Speed, well, either you write the machine code yourself, which takes you a lot of time and money, or preferably you write it in assembler so that you can make the most use of the optimizations, but again, that takes time and money. So even better, you write it in a compiled language, which you write your code, you write a small amount of code, and it generates fast machine code, which runs in the native machine code language for speed. That's why games written in C++ are going to run faster than games written in Python for speed, because it's compiled rather than interpreted. Portability, well, a compiled language is only ever going to run code on the processor it's designed for. If you try and compile your C++ for use on Linux, it might end up not running on Windows, or it might not end up running on a Mac. Or definitely, if you compile it for a ARM processor, it's not going to work on an Intel processor, and it might not work on an AMD processor. You don't have portability. If you write it in Python, well, it might run slower because it's interpreted, but you can interpret it on the fly on whatever platform you're on. So a big advantage of something like Python is, well, you can run it anywhere. It's portable. Interactivity. So if you want to change your code whilst the code is running, then you don't want to have to wait an hour to recompile it. If it's translated, as soon as you save your source code, it's ready to run. Okay, it might run slower, but you've got to wait less time to compile it because you don't have to compile it at all. Error handling, well, things like assembler will have very little error handling. If something crashes, it's going to go catastrophically wrong. A compiled language might not handle your memory management all that well, and it might be difficult, but your slow interpreted language like Python is going to be very reliable in the way that it handles errors. There are going to be fewer runtime errors to have to deal with. Interpreted languages are way easier to test and debug because if you imagine sitting in Moo, typing out your Python code, and then pressing run and waiting for 5 minutes before you test it, it's really draining and it's very inefficient. The beauty of Python is you write a line and you test it instantly. And then you write another line and you test it instantly. So debugging and testing is dead simple when an interpreted language. It's much harder on a compiled language. Secrecy, don't really know why that's there, to be honest. But if you have to hand out your Python code to your clients, well, they can see the source code. They can change it. If you've got a proprietary algorithm that does decryption or encryption or something like that, and you're selling that, well, your customers can then see your secrets. They can see your source code. They can change it. They can sell it on. It might be illegal to do so, but it's a lot easier for them to do so. If it's compiled, you can obscure it, so they only get the machine code. They can't see the source code. So Windows is a good example of a compiled operating system. Microsoft don't like and don't want people to have the source code for Windows for security reasons, because if you could have the source code, you could work out how to make viruses that make use of the closed source weaknesses in Windows. If Microsoft suddenly decided to develop Windows in Python, it would save Microsoft a huge amount of money because they'd have to spend less time developing it. It'd be easier for them. But Windows would be even slower than it is already. And viruses would be all over the place because everyone would be able to see the source code. It would not be secretive, and Microsoft would lose a huge amount of money. So how do you choose? Well, basically you go through all of the things that we've had already. Let's have a look. Oh, I didn't open the thing. Sorry. My apologies. We're going to open up P10. Oh, I did open it up. Here we go. And we'll watch this together. If you're at home, you can watch it yourself. I'd like you to fill in the gaps on here. So I'm not going to include the video in this recording. You can watch that yourself. If you want to go straight to the answers, then 3 minutes 30 will just be a summary of this table. Or you've got the PowerPoint that explains the advantages and disadvantages of each. The point is, it's not fair to say that one is better than the other. They're both good for different purposes. Interpreters are more flexible. Compilers produce more code that runs more quickly. In a nutshell. So the final activity here is where you're given a scenario and you have to work out, are you going to use assembly? Are you going to use a compiled language? Or are you going to use an interpreted language? So let's choose one. Here we go. The logic of the program must not be known by the user. The logic is secret. So let's say you've got an algorithm for predicting stock market exchanges, and it buys and sells on the stock market automatically. Your algorithm might be really simple, but it's still secret and you don't want your competitors finding out. That rules out interpreted because you don't want to share the Python code or the Lua code or the R code or something. So that means that we could either have assembly, a low-level programming language, or compiled. But activity 3 just gets you to choose between compiled or interpreted, so it's definitely going to be compiled. The important thing here is that this might be a 3-marker, maybe 1 mark for saying which one you think and 2 marks for a justification. So why would compiled be better? Well, because compiling obscures the source code. You can't see the original source code, which you would be able to see in interpreted. So that means that your customers wouldn't be able to see the logic, but they would still be able to run compiled code with the added benefit of it probably running a bit faster. All right. Once you have finished, I would like this to be saved and uploaded. Let's have a look and see where. Yeah, can you upload it to half term 8 issues and impact 2 for me, please? Make sure you save the Word document before you upload.